Hello and good morning. Thank you so much for joining us today for this week's session of the Parks College Weekly Webinar Series. My name is Amy Price and I'm the Outreach Coordinator here at Parks College. I'm joined today virtually by Dr. Andy Hall and Prathamesh Bhagavath, who will be showing us around the Surgical Robotics Lab. We're so excited to have you joining us today from wherever you might be. Thank you for taking the time to visit us virtually and to learn more about the biomedical engineering program at St. Louis University. In total, Parks College has programs available in aerospace, biomedical, civil, computer, electrical, and mechanical engineering, as well as flight science and aviation management and engineering physics. We hope that you'll see or hear something today that piques your interest. Before we start, I want to give you an idea of how the webinar will flow. I'll soon introduce Dr. Hall, who will be showing you around the lab space and sharing information about the biomedical engineering program. He will then introduce Parks students Prathamesh, who will share his experience of being a biomedical engineering student with you. And finally, we will include with some time for questions and answers. You can submit any questions you may have throughout the presentation to the Q&A feature at the bottom of the screen if you're viewing through Zoom, or in the comments section if you are viewing through Facebook Live. And we'll do our very best to answer as many questions as possible during the last 5 to 10 minutes of our session. Throughout this webinar, you don't need to worry about turning off your microphone or your camera. You can hear and see our presenters throughout the webinar, but we cannot hear or see you. Finally, if you have any technical difficulties during the webinar, please email parksevents@slu.edu and we'll do our best to address issues that arise. The session will be recorded and posted to our YouTube page by tomorrow, and you will receive an email with that link when it becomes available. And now, with all of that housekeeping out of the way, I am happy to introduce Dr. Andy Hall, a faculty within our biomedical engineering program, and Prathamesh Bhagavath, a biomedical engineering PhD student and the Surgical Robotics Lab. Dr. Hall and Prathamesh, I will turn it over to you now.
Good morning. Well, Dr. Hall, Prathamesh is a graduate student in my laboratory. So what we're going to try to talk to you this morning about is...
Sorry, I'm going to jump in. Could you guys get a little closer to the microphone, please? We're having trouble hearing you.
Oh, good. And we need to make, let's see, how do we make our video big? Do you do that or do we do that? I'm not used to this format. Hey,
oh, I can do that. I can do that, yeah.
Okay. All right. Good morning. All right. Can you hear us better, Amy?
Yes, sounds good.
Perfect. Okay. I'm Dr. Hall. This is Prathamesh.
Hi.
So, biomedical engineering is an extraordinarily broad field, but what we're going to talk to you about today is biomedical robotics, and specifically surgical robotics. And so what that means is that there are procedures that have been done for years and years and years by hand that we're trying to bring robotic control to. This is not unlike what's been done in the automobile industry, where people used to put cars together by hand, and of course robots do a huge part of car manufacturing today. Yeah, you can go to YouTube and see a million videos on robots making cars. Now robots are starting to encroach into the operating. We're trying to do let's see, go ahead and show them the robot. This is a German robot made by a company called KUKA. And it is a very functional, very smart general purpose robot. And so what we're trying to do is adapt this robot to do robotic spine surgery. And robotic spine surgery, here's your spine. Sometimes these discs will degenerate. And when that happens, then your spine moves around when it shouldn't. And the problem is that the thing that's in here is your spinal cord. And so when vertebrae move relative to each other, that causes a lot of pain. And so one procedure is to take screws, put them in your spine, and then connect those with rods. What that does is it locks them together so they can't move. And that's why that procedure is called spinal fusing. You're fusing two vertebrae into one. And so that can, in many cases, can alleviate the pain. And so this is a procedure that is traditionally done manually that we're trying to do with a robot. And it's, yeah, we're still working on it. It's an area of research. And so what we're going to try to do is demonstrate that to you now. Okay, so put that there. Okay, are we ready to start? Yeah. Okay. So robots are run by software. So we wrote a bunch of software to tell the robot what to do. Okay. So the first thing the robot's going to do is to grab a tool that allows us to do something called registration, which I'll tell you about in a moment. Okay, so it's going to go down, it's going to pick up the tool from the top. We use magnets to hold the tool to the robot. And so now that the magnets have engaged, now we take the tool out of the rack. There we go. Okay, and we put it. Okay, now the reason we're going to do this process is because I want to show you something else. Okay, ready? All right, we're taking this laptop on the road. Okay, this isn't it. What we're doing is called right here. Okay, what we're doing is called image-guided spine surgery. What that means is we don't look at the patient and say, I want to put a screw here. We look at a preoperative image of the patient, a CT scan, for example. We plan the surgery on the CT scan, and then based on that plan, then the robot knows what to do. But in order to do that, think about this. CT scans, this one, for example, right? See this is a CT scan of our phantom, right? Of that green thing that's out there that you just saw. We'll show you again. So that's the image. And so this has a coordinate system, right? X, Y, Z. And then the robot has its own coordinate system. So in order for the robot to know where this thing is, we have to go through a process called registration. And we've identified certain markers on this phantom in the image. We're going to go touch those on the robot so that we can match those two spaces. And once we match the two spaces, then the robot knows where to put the screws that we've identified here. So let's go do that. Right. Perfect. All right. Amy, tell us if you can't hear us. I'm trying to talk loud, but also show the picture.
It sounds great. Thanks.
All right. So we're going to go touch some points. And to do that, this is something called a collaborative robot. A lot of robots, when the robot runs its program, you have to leave the room or put the robot in a cage because it doesn't understand humans, or it would knock humans out of the way. This robot is designed to work with humans, like physicians, surgeons. So it's going to go into a so-called hand guiding mode so we can move the robot where we want it to go. All right. Great. So see this? It's just like it's floating in space. All right. So we're going to go touch these points so that we can register these two spaces, these two three-dimensional coordinate systems. All right. Good. All right. We'll go to the next point. Okay. Okay. And okay. Good. Forward is here. Okay. What we're doing is the robot is recording a position in three-dimensional space where this marker is. And so once we do that, then I'll send over the markers from the computer that we got on the image, and that will allow these two three-dimensional coordinate systems to be registered. Good. Okay. All right. Oh, we're going to do this over here? Okay. So all we're going to do is we are going to, it's on, good. We're going to say send over the fiducial markers. Okay. Looks like we just sent, oh, do you have to push a button that says go? There we go. Now, now the robot's going to put the registration tool back. And the robot now is going to get ready to place a screw in our phantom, right? When you're developing something, we don't actually, the first thing we do isn't get a human and try to put screws in the spine, of course. We operate on what are called phantoms, which are test objects. This test object, we took over to the CT scanner, and that's why we have an image of it. Also, you can see that it was 3D printed, and I'll talk more about 3D printing in a moment. Is it ready for a screw? All right. Okay. Screw one and all right. It's going to pick up another tool. This time it's going to pick up a drill. Before you can put a screw in, if you've ever worked around the house, you have to drill a hole. So the first thing we're going to do is we're going to drill a hole in our phantom, our pretend spine. Again, because we did the registration, because we registered those two spaces, the robot now knows where to go. So it's going to get itself all oriented. See that? Then it's going to approach the place where we told it to go. Now, the phantom already has a hole in it, so that we don't drill a new hole every time, but you can see we're now drilling a hole. Again, this is the demonstration phantom. So while that's happening, it takes a while. Let's talk about 3D printing. So you can see all these colorful tools here, these plastic tools. Every one of these was 3D printed, okay? These tool racks like this, they were designed in a CAD program and 3D printed. This drill, all of these tools here. So we 3D print lots and lots of things. The reason we do that is that it accelerates our development. There's lots of reasons to do 3D printing, but it's particularly valuable in R&D. You see these tools here that are now made in stainless steel. These cost several $1,000s and several weeks to make. But in order to figure out exactly what we wanted, we had to print 10 different versions of this, and we did it in 3D printing. And so what 3D printing allows you to do in development is dramatically reduce the cost and dramatically accelerate your development. Because if this takes thousands of dollars and weeks to print, every time we went through an iteration, we would have to wait and pay a lot of money. 3D printing, we can make a different design every single day. So all we do is figure out what we want, change the CAD program, and print it overnight. And the next morning we come in and we have a new tool. And the tool costs $5, not $1,000. So 3D printing is a critical element. Now, the other thing that I'll tell you is that SLU has a brand new 3D printing center called the Center for Additive Manufacturing. It was a result of an internal grant. It has its own space in the Interdisciplinary Science and Engineering building. So there are about a half a dozen 3D printers over there. Some that are really simple that students can have direct access to and just go in and print. Others are, $200,000 units that you can have the staff there print things for you. So they also hire student workers. So we can print plastic like this. We can print polycarbonate. We can print carbon impregnated nylon. We can also print, one of the printers is also color. So you can print different colors and different hardnesses. So there's a huge variety of things you can 3D print at that center. It's brand new. So it's still shiny building over there. And so in addition to offering education, another thing that the center will offer is a certification. So one of the big printer manufacturers is Stratasys. We have printers from them. They offer a certification program that you can go through, become a certified 3D printer expert, and that goes on your resume. So this is a brand new offering for SLU in this area, and this would be something you would do in addition to your regular engineering work. So yeah, we're pretty excited about that. We started with a bunch of really small printers, a CAS low spot if you're into 3D printing, and so that's a $3,000 printer. But now a lot of our work we send to the center because these are bigger, more reliable printers with a lot more capability. Okay, so we're drilling our hole. We're almost done. You can see if we had a bone, we wouldn't be able to see what's going on, right? Because the drill would be in the bone. But we made our phantom so we could see what's going on. Here's our target, this little pin right here. Okay, so the drill is going from here to here because on the image, that's what we told it to do. Okay, it's almost done. Okay, put that back right there. Thank you. Prathamesh is, he's a PhD student, and he comes to us already with a master's degree. So he came as a fairly useful guy. And so, but he's going to study here for the next 3 years and finish his doctoral studies working on this robot. Come around. All right. Hi. So he and I, the very last part of the work on this particular project, he and I did together. We had to do it just like this with masks on because the virus was already here. And so, and then we did the last part of the work to submit this to an engineering journal, the IEEE Transactions on Medical Robotics and Bionics. So he and I worked on this together. And so as a PhD student, he also has a leadership role in the lab. He has to work with undergraduates and graduate students to help them do things with the robot and other projects. So actually, that's one of the nice things about SLU engineering and biomedical engineering in particular is that there's an opportunity here for undergraduates to work in the research laboratories, perhaps more so than other universities, where we do the professors here do a combination of teaching and research. And so because we're not huge and because of the way we operate, undergraduates have a really good opportunity to work in the research labs, usually starting around their junior year. So something to keep in mind. Okay, almost done. Are we there yet? It's pulling off. Right. I'm like a kid on vacation in the car. Good. Okay, so we are leaving the bone, simulated bone. Amy, how much time do we have?
We are good. We have about 12 minutes. And actually, Dr. Hall, I have a question for you. So over the past 10 minutes that the robot has been drilling, is this in real time as it would be for a surgery?
Yeah, exactly right. Yeah.
Wow.
We drill very carefully because the robot can measure what's happening. It can measure the torque and the force that it's applying and make adjustments based on that. And that's just software that we're developing. So yeah, this is exactly how it would go. Now, it's possible to make it faster, but right now we're being extraordinarily careful. So yeah, this is exactly what would happen in a patient.
Very cool. Before you go on to the next segment, if anybody has questions, feel free to submit them to the Q&A or to the comment section on Facebook. All right, I'm going to disappear again.
All right, here we go. All right, we've drilled a hole. Now we're going to pick up a screwdriver tool. Then we're going to get a screw, and then we're going to put it in. Now we have a kind of wacky screw here. This is all the screws that I have, the proper ones, I've already put in bones for our research paper. So I have kind of a lame screw here, but we'll make it work anyway. All right, we use the same exact mechanism. We use magnets to hold the tools to the end effector or to the end of the robot. And then once they attach, then we slide them out of the tool rack. And that's what we're doing here. What's interesting about robotics, you already may know this, it's an awesome combination of a lot of different fields, right? You can see there's mechanics involved in designing all these end effectors. There's medicine involved because you have to understand the procedure that you're doing. But there's also a ton of software. Robots are controlled by computers. And so you have an opportunity to write software. Some of the students that are working in the lab are actually pursuing computer science as either a minor or a double major. And that's an awesome combination as computers more and more and more enter into the medical field. Okay, we're picking up the screw. Hopefully they can pick up the crazy one here. Is it happy?
Yes, it is.
Okay.
It is picking it up.
Okay, good. Okay,
Yeah.
now it lifts it out. Again, that we want the process to be, oh, that worked out well. The process to be completely automated. So, no hands. And what this, if you can completely automate a process, the other thing you can do is you can make the process remote, right? Aside from the registration, which we can also make hands-free, we're not doing anything, right? And so you can envision an expert spine surgeon using the robot in another country to perform spine surgery, right? This could all be done with a computer over the internet. So that's another thing that robotic surgery enables. All right. We have a screw. It's on the end of a screwdriver. Now we're going to go over to the spot. Again, the spot was defined on the CT image, but because of the registration we did, the robot knows where to put it. So it's coming over here. It's coming over to the hole that it drilled. And now, oh, nice work, Prathamesh. It's going to put the screw into our phantom. And there it goes. Now it's done. Now we have a special mechanism that allows the screwdriver to retract while locking the screw in place. There we go. So this actually is a coaxial screwdriver mechanism. So there's an inner shaft and an outer shaft. And the inner shaft locks so that the screw can't move while the outer shaft disengages from the screw thread. Very nice. So because this hole was already here, this guy rattles around, but normally it would be locked in place, sort of like this. Or this. Okay, so we are, okay, go ahead, you can go ahead and put it down. We're essentially done with this demonstration. So in the development of this thing, the first thing you have to do is show that it works. One of the key things to show that it works is it accurate, okay? And so, in other words, if I tell it to put the screw in a certain place, how close does it come to putting the screw where I told it? Hey, so, put that away, good. And so the way that you do that is you take a separate image. So if I put the screw in a bone, which we've done, I take this whole thing, I go back to the CT scanner and I scan it, and then I take the preoperative image and the postoperative image and I register them, right? And then I compare the actual screw location to the planned screw location. And I do that on that same computer that we showed you. And so then you can measure what's my error, because that is an absolutely critical specification, right? How accurately can I put screws in? This particular system, the accuracy of putting screws in is less than 1 millimeter. So it's a pretty accurate system. Okay, let's see. So this is one of the things we do in this lab. We have some other smaller robots that we work with. We work with some other. We're developing something called microspheres for embolization of prostate cancer. We are working on artificial tissue that fits into 3D printed molds. Those molds have come from CT scans of patients. So there's a number of things we do in the lab. But this is the biggest one, physically. So I think we're good there. And so Amy, is now a good time for questions?
Yeah, this is a great time for questions. First, thank you guys so much for this demo and for taking us in the lab. How cool. For anybody viewing, please feel free to submit your questions. Dr. Hull and Prathamesh, we have a question already. So if robots do 3D printing, would you have to spend more money? Would the process take longer, is the question. So I think talking about the 3D printing process and the costs associated with it and the time requirements.
This is 3D printing done by a robot? Is that what you mean?
That was the question, but yes, I think within a 3D printer, you know, if you need a specific tool or part that's 3D printed, you know, what's that look like financially? And also, what does that add or subtract time-wise from traditional methods?
Okay, I'm a little confused.
Can you talk more about how you use 3D printing to develop some of the tools used with the surgical robots?
Oh, sure, just these?
Yeah, yeah.
Sure. Okay. So, right. So we figure out what we want, and then you have to go into a CAD program like SolidWorks or AutoCAD, and you design this, and then then you can process that file and send it to the 3D printer, and then we evaluate it with the robot, and then based on the results of that, we can modify the design, or in the end, we take that exact same design to a machine shop and have it made out of stainless steel. So, and again, the value of 3D printing is to be able to rapidly iterate through designs. Because when you're doing research, the first time you look at something, it's unlikely that it's going to be the final product. And so you want to iterate through designs until you get what you want.
Gotcha. So 3D printing is especially helpful in the research and development phases. And then by the time it actually gets to use in a medical setting, those prototypes, the designs would be finalized.
That's correct.
All right. A question that we've heard before is, has this specific robot been used in surgery?
So this is a general purpose robot. The reason that it's white, not orange.
Oh, Dr. Hall, we're having trouble hearing you, sorry.
That's all right. The reason this robot is white and not orange, which most industrial robots are, is that it's specifically been developed and marketed for medical use. And so there's just now beginning to be some commercial uses of the robot, in this particular robot in medicine, not spine surgery yet. We're the first to develop something for spine surgery, but there's other fields where this robot is being used. So this is increasingly used for medical applications, and not just surgery, but all sorts of medical applications. So yeah, it's a very capable, very useful robot.
Awesome. Another question just came in. How long does it take a robot to process the research and complete the design? I'm going to rephrase that. How long would it take a robot to perform, for example, the spinal fusion surgery compared to traditional surgery done by a surgeon?
Sure, it's the process is highly variable, and also the screw placement process is only a part of the overall procedure. So we could maybe cut it in half, and so there's some efficiency there. Although I would say that's probably not the primary value. The primary value is to there's a few other things that are more important. One is that once the robot is doing the procedure, the robot can sense force and torque in ways that a physician can't, right? It can sense that quantitatively, and it can make adjustments in what it's doing with machine learning algorithms, for example. So the measurements from the robot can go into algorithms that can tell the physician how well it's doing. Did it run into a defect in the bone? Does it think that based on that, should we put in a different screw, one with a larger diameter? And so these are quantitative things that can be processed in real time that surgeons would have to do more qualitatively. And so that's one advantage. Another advantage is precision, right? So the robot should get it right every single time. And so it should eliminate human error. And then I also mentioned the idea of being able to do remote procedures. So these, probably more than speed, are the values of this kind of technology.
Excellent, thank you. One last question. What programming languages do you use for your software that you're building?
Sure, we use a number of languages. We use the languages that need to be used. The primary languages we're using here are Java and Python.
All right. Well, everyone, that is just about our time for today. I want to send a huge thank you to Dr. Hall and Prathamesh for taking us inside the Surgical Robotics Lab, for showing us that really cool demo that I'm sure not many of us have seen or thought of previously. So thank you both for that. If you would like to learn more about the biomedical engineering program at SLU, please visit slu.edu/parks. And we hope that all of our viewers will join us again in this space next week on Wednesday, September 16th at 11 a.m. for a visit to the Structural Engineering Lab with our Civil Engineering program. Thank you again for joining us. Have a great day.
Take care.